Hi all, now we're heading into section 2.3 in the Rogowski text, and this section is titled Limit Laws and Using Algebra Manipulations. There's not much algebra manipulations you need in this chapter though. As I say here in the subtitle, aka worst section in the book. That's because there's really not much to do in this section. It's ridiculously easy section. You will hate it as I do. So why are you going to hate this section because it's so easy? Well, here's what makes it so easy. We're evaluating limits similar to what we did in the last section in section 2.2 numerically, and like what we will have to do in the future, where we will have to use algebraic manipulations because the limit's not going to exist or the function's not going to exist at the value where we're trying to take the limit. However, every problem in this section is going to be continuous and defined at the point at which you're taking the limit. Whenever that's the case, you can simply just plug x equals a into the problem and make a direct substitution. So for example, if I ask you to find the limit of 4x as x approaches 7, you'd say, well, as x approaches 7, we know that the y value is going to approach 4 times 7. It's going to approach 28. Now, it doesn't matter whether I'm approaching 7 from the left-hand side or from the right-hand side. Either way, that limiting value is just going to be f of 7 or 28. So anytime you can plug the value into the function, you should, and that'll be the limiting value. Now, notice our next one here, this one would confuse some people because they're like, well, wait a minute, there's not an x to plug in. There's not. So think about that. If you have the function f of x is equal to 10, and I say, well, what is the y value approaching as x approaches 5? You'd say, well, it doesn't matter what x approaches. The y value is always 10. So again, you can think of it as, well, he's technically plugging in the 5. It's just that there's nothing to plug into, and he's getting an answer of 10. For my next one, I know a quadratic is nice, continuous, and defined for all x values. So I would simply just plug the 4 into the limit as x approaches 4 of 2x squared minus 3x plus 4. I'll get 2 times 4 squared minus 3 times 4 plus 4. That gave me 2 times 16 for 32 minus 12 plus 4. This has a limiting value of 24. Now, the 3 rules that I've used on this page are the limit as x approaches a of any constant is just that constant. That's what I showed right there. That's the associated limit law for constants. Well, the coefficient rule, which is what I was trying to show up here, is that it doesn't matter what the coefficient of x is. All you do in order to apply the limit is just to plug the value of x in, multiply that coefficient, and get your answer. That's why it's saying the limit as x approaches a of k times f of x is just k times whatever your function is evaluated at the value of a. And then the last case, well, what if you have a sum and difference of several different terms inside your function? Well, you just evaluate each of them at the limiting value, in this case at a, and then just add or subtract them together depending upon whatever they are in the problem. In general, whenever a function is defined at x equals a, the limit as x approaches a of f of x is simply f of a. Okay, so if I gave you a function that is not necessarily continuous everywhere, if I wanted to ask an interesting question here, and this section does not ask interesting questions, but hypothetically, if I did, I would ask you what's the limit as x approaches negative 5. This rational function does not exist at negative 5, so you would have to analyze what happens as x approaches negative 5 from the left, what happens as x approaches negative 5 from the right. I believe in that case, you'd find the overall limit does not exist because one side's going to go to negative infinity and the other side's going to go to positive infinity. Okay, but for this problem and every problem in this section, they're not fun. What does that mean? This function is continuous and defined at the value of x equals negative 2. Can I just plug it in? Sure you can. 3 times negative 2 minus 7 over negative 2 plus 5. You'll get negative 6 minus 7 is negative 13. We see our denominator is going to be 3, so we get negative 13 thirds there. Now, the associated limit law that you'll see in the book for this section says that, well, if the limit as x approaches a of f of x over g of x, that's just going to equal f evaluated at a divided by g evaluated at a. Now, of course, this is only valid as long as the denominator is not 0 at the limiting value. That's why I said this would be a more interesting problem if I were to evaluate this, the limit as x approaches negative 5. I couldn't simply just plug it in here. This quotient law would not work. Now, for the next one, it's a limit law for products. You just say, well, can I plug a 4 into each one of these terms? Of course you can. It's going to be completely defined. So I go ahead and do that, and I can say, well, when I plug a 4 into the first one, I have my 1 plus 4 to the 3 over 2. I plug a 4 into the second one, and I have 4 plus 4, and that whole group raised to the 2/3 power. Okay, so here's how I simplified this. This first one, I just said, well, 4 to the 3 over 2. That means the square root of 4 cubed. Square root of 4 is 2. So I've tried to show my work here and say, well, one step there, I can get rid of the denominator 2 by taking the square root, and I'll have 2 to the 3rd power. Of course, that's going to be 8. I'll have 1 plus 8. That's where my 9 comes from in the next step. Over here, I know that the power is on the outside of the parentheses, so I had to add the 4 plus 4 first, and I got my 8, and then I have 8 raised to the 2/3 power. Well, that means the cube root of 8, which is 2, and then 2 squared would be 4. So we end up with a final product of 9 times 4, 36. That's using the limit law for products, which just says if you have a product of functions inside of a limit as x approaches a, you just say, well, then evaluate both of the functions at a and multiply them just as they were multiplied here. In the last few problems in the section, they will tell you a specific value for a limit, such as this, where they say, what if I know that the limit as x approaches 6 of f of x is 9? And that the limit as x approaches 6 of g of x is negative 3. Okay, so that gives me information about these two. Now, then I can use the limit laws to evaluate the limit as x approaches 6 of 3 times g of x minus 5 times f of x. Well, all I have to do is just say, well, anytime it's inside of a limit as x approaches 6, I know that I can replace the function g of x with a negative 3. That's exactly what I do. So 3 times g of x becomes 3 times negative 3. Then I have minus 5 times the limit as x approaches 6 of f of x, which we know is 9. So all I do is I substitute what these two are equal to in our problem, and then it's just arithmetic after that. We have negative 9 minus 45 for minus 54. The next problem here, it's the same idea. We're still using this information. I know that within a limit as x approaches 6, f of x is going to go to 9. I allow that in my answer. Plus 2. Over my denominator, that's the limit as x approaches 6 of g of x to the 3rd. I can say, well, a limit as x approaches 6 of g of x is negative 3. So I'll replace the inside part with negative 3, but that negative 3 is now being cubed. That's going to give me a negative 27 in my denominator. My numerator was 11. I would prefer to write the final answer with a negative in the numerator, though of course it doesn't matter. My answer was negative 11 over 27 there. For the last one here, I had the limit of 1 over the square root of 3f of x minus 3g of x. Again, you say, well, we already know that anytime f of x is inside of a limit as x approaches 6, it's going to be worth 9. So you see I replaced it with a 9 in the next step. Minus 3 times the limit as x approaches 6 of g of x, we know is negative 3. So I had inside that square root 3 times 9 minus 3 times negative 3. That ends up giving me 27 plus 9. And I know 27 plus 9 is 36, so we ended up with 1 over the root of 36, which is 1 over 6. Now, you're thinking, there's got to be more to this section, right? Sadly, no. This is, like I was saying, the worst section in the book. You probably should get through your homework in this section in probably 15, 20 minutes maximum. But there are better sections to come, so never fear. But please do let me know if you have any problems with this section. I would imagine we can clear it up for you in no time at all. All right, guys, take care.